In this video, let's look at more examples of the conservation of energy as applied to falling objects. So basically in that last video, we had a look at one of those types of examples, but gradually now we'll be adding more aspects to the question that can be asked, and we'll also be gradually adding more levels of complexity to the ideas we've discussed in the previous video. So this time as well, let's talk about that same spherical objects. Remember that last time we also did an example regarding air resistance being present. This time let's make our object start from here. So let's say this object is dropped from rest, and let's say the height from which this guy is dropped, which is going to be this height. So this height, let's say that height is 20 meters, and when this object hits the ground, so when it hits the ground, it's moving with, let's say, velocity 15 meters per second. And this is kind of very similar to the last one, only this time this is dropped from rest and not thrown up. The question is the same: find the magnitude of the average frictional force or air resistance acting. Right? So remember how we did this question in the previous video is you know that if there is air resistance or any sort of frictional force acting, it's going to be taking energy away from our system. So what I can do is I can find the initial value of the energy at this point. Let's call that EI. At this point, again, this is also simple in this way that the initial energy or the final energy is either only gravitational or kinetic. It's not a mix of both. And that is one of the examples we'll be doing towards the end of this video. Let me also give you the mass of this object because I forgot to do that. So let's say that the mass of this object is 2.0 kg. So I can find the initial potential energy now. So mass is 2, small g is 9.81, h is 20. So I can find out the initial value of the energy, which is 392.4 joules. Similarly, I can find the final energy, which is only potential, only kinetic energy, my bad, because this is literally at the height from which we are measuring. This is literally at the point from which we are measuring the height. So no potential energy here. So half into 2 into 15 square, which is just 15 square. And if my mental math serves me right, that's 225 joules. Obviously, the initial and final energies are not equal. That means that energy is lost. So that loss in energy is basically because of the work done against the air resistance, assuming it has a constant magnitude, which usually it does not because the speed would be changing. So that is F, and the distance it acts through, as this guy would be falling downwards, is 20. So F into 20 equals to the difference in energy, 392.4 minus 225, which is 167.4. So 167.4 divided by 20 would be some answer around 8. So that is 8.37, or you can say 8.4 Newton, correct to 2SF. Now let's do a slightly different type of question. The idea would be exactly the same, only the phrasing of the question would be slightly different this time out. So let's also set up the question in the same way. Let's say that this time, so let's say in this case the object is again thrown up, but instead of speeds and all of that, maybe the examiner gives you something like the values of the energy here. So it says that this guy from here, it was projected with some kinetic energy. Let's call this 50 joules, right? And it says that in going from this point to this point, the change in potential energy, which is obviously positive because it's rising, is positive, let's say positive 30 joules. And additionally, it also says that in going from here to here, the work done against friction is 15 joules, and you have to find the kinetic energy at this position. Let's call this position 2. Right? Now, how would you do such a question? So here, obviously, this guy is not at rest, and that's why you are being asked for the kinetic energy at this point. So how do we do a question like this? A lot going on here. So I can see that the initial energy is basically 50 joules, and finally the energy would be the 30 joules of what do you call it, potential energy, which has increased. So if here it had no potential energy, then here I can say that the value of the potential energy is 30, and let's call the missing value of the EK E, right? So I know that the loss in energy must be because of this. So I can set up a very simple equation, and this is all there was to this question. 50, the initial energy, minus the final energy, 30 plus E, should equal 15, right? So this becomes 50 minus 30 minus E equals 15, right? So 50 minus 30 is 20, minus E equals 15, and from here E eventually turns out to be 5 joules, right? So my thinking was this, that basically in going from here to here, if there was no kinetic energy here, this would have been very easy, right? So I would say that the amount by which this decreases should have also been 50 if this were at rest. So then it would be that all of this 50 must have been converted into the potential energy here, but if it's only increasing by 30, so it's just 20. But the idea here was that it at this point it also has some kinetic energy, right? So you can also think of it this way, that this 50, and this is ultimately a matter of preference, that the initial energy 50 minus the work done is the energy at this point. So you can also say that the energy at this point must be 50 minus 15, which is 35. If 30 is coming from the potential, then the remaining 5 must be in the kinetic energy. Let's now go on to a very complicated question. This type of question is almost never asked, but you might also take this as a challenge for yourself. And this is a question which has like multiple aspects to it. So in this question, let's say that this is what the diagram is like. So this object at this position is already moving with some speed 2 meters per second to the ground, 2 meters per second downwards, and at this instant it's 50 meters above the ground. And at some other instant afterwards, when it's 20 meters above the ground, it's traveling downward with some speed v. The job is to find v. Additionally, we also know that a constant frictional force of 5 Newton acts on this object when it is moving upwards. Right now, how do we start doing this question? Again, we know that obviously the final and initial energies will not be equal because of the work done against this. So I can just go ahead and first start with the initial energy. Now, what makes this question a bit more challenging is that initially or finally, the energy is neither purely kinetic nor purely gravitational potential. It would be both. So initial energy is mgh plus half mv square, both mgh, if I just write this here. Okay, can I just grab this? Yeah, I can. So mgh, okay, again, I forgot to give you guys the mass. So let's say that the mass is 0.8 kg of this object. So 0.8 into small g, which is 9.81, into h, which is 50 plus half into 0.8 into 2 squared, and I'll find this value. This is the value of my initial energy. So 0.8 into 9.81 into 50 plus half into 0.8 into 2 square, which turns out to be 394 joules for me. Now again, it's up to you. As long as your concepts are clear, you can do this any way you see fit. What I'm going to say next is that the final energy will be the initial energy minus the work done against the resistive force, which is 394 minus the work done. So a constant frictional force of 5 Newton acts. What distance does this force act through? Which is this, which is 30. So that is minus 5 times 30. So that's 394 minus 150, which is 244 joules. All right. And now I know this is the value of the final energy, but again, that final energy is also not just kinetic, it's this potential plus this kinetic. So now I'll start setting up the expression for this. So I'll say that the half into 0.8 into v square plus the mgh, which is 0.8 into 9.81 into 20, this must equal the 244. And from here on out, I just need to make my v the subject of this equation. So 244 minus 0.8 times 9.81 times 20, this is 87.04, which is equal to 0.4 v square. So 87.04 divided by 0.4, taking the square root, v turns out to be 14.8 meter per second as the speed of this object. So this one actually had a lot of aspects to this. Very, very rarely such a question is asked, but still I feel like it's a fun question to do given just how challenging it is. So in the next video, we'll now start looking at the conservation of energy questions related to tracks and slopes, because those are also very often asked in your past papers. I'll see you there.